It is essentially time for us to get started, so I want to do so. We have been covering some properties of real numbers, some facts about real numbers, in particular that have to do with inequalities. So we've defined what it means for one number to be less than another number. We've defined what it means to be a positive number. And we've had a few facts about inequalities. I want to take a few minutes and ask if anybody has any question about anything that we've covered so far. Anything they want to ask about. It's okay to ask anything. It's okay to ask nothing. Okay, let me say this. Please make sure that you can do the material we're doing, that you understand why the proofs are true. Okay? And what I'm presenting here isn't necessarily the only way to prove something, okay? But they are proofs. Does anyone have any questions of me before I start on new material?
Did you get the 100% last class?
No, I did not. We are to a spot where we're getting very close, I should say, to getting a homework assignment. But we haven't gotten one yet. It won't be very far off in the future that we'll get our first one. Anybody else with a question or comment? Okay. Well, we had a fact earlier that had to do with if you give me a positive number, that meant that it was greater than 0. I want to look at an analogous fact today. So I want to start off with this. If minus A is an element, I'm sorry, I'll write it down this way. It's a fact. A minus A is an element of the positive numbers. If and only if minus A, A is less than 0. That's all right. So if your minus A is a positive number, that meant that A itself was less than 0, and vice versa. So this fact is an if and only if statement, and therefore we're going to have, in its proof, 2 directions to go. This is the forward direction, that is, we'll assume or suppose we'll let minus A be a positive number. What we want to show is that really that A is less than 0. What does it mean for A to be less than 0? How can we show that A is less than 0? Well, the way to show that A is less than 0, one way to show it.
0 minus A is an element of positive numbers.
Yes, that's right. That is a way of showing it. 0 minus A is positive numbers. Well, here, note, minus A is the same thing as 0 plus minus A, because 0 plus something is just the sum. So 0 plus minus A is minus A. Is that okay with everybody? But that's the same thing because of the way that we define subtraction. 0 plus a minus A is the same thing as 0 minus A. And this is the same thing as minus A. Okay? What do we know about minus A? The only thing we're assuming about minus A in this direction is that minus A is a positive number. So that means that 0 minus A is positive. Why am I writing this statement? Because minus A is positive. And minus A is the same thing as this guy. And since minus A is positive, this guy is positive. That's the same thing as minus A. Well, since 0 minus A is a positive number, that means that 0, or A, is less than 0. And 0 is the bigger of the two. Is that okay with everybody? That's by definition. So that's the forward direction. Let me give everybody a second. Look at it. We'll go the other direction. What is the thing that we're trying to prove when we say we're trying to prove the other direction? We're trying to prove if, then. That's right. So here, we assume or suppose, that's right, Megan, that A is less than 0. We want to show that minus A is a positive number. Okay, well, since A is less than 0, then what can we say? What's the definition of less than give to us? What can we say? 0 minus a is a positive number. That's by definition of less than. That's exactly right. Okay, what is 0 minus a? Well, 0 minus a is really just, if you simplify that, that would be minus a. And that's what I wanted to show, is that minus a was a positive number. So that concludes this proof, and remember, this is my symbol for we're done. We've shown what needs to be shown. I just wanted to write that down. This may not be the only way to prove it, but it is a way to prove it. Anybody with any questions about that? Okay. Well, I said that we had a theorem upcoming that was of interest to me, and just it's kind of stunning what we're going to prove here. We're going to prove something that everybody said, well, we know this is true, but we're going to prove it based on facts that we've already done or will do, and the algebraic properties of R. So here's the theorem. It's got 3 parts. It says if A is a real number, then A squared is greater than 0. Part B of this theorem says, well, 1 is greater than 0. And part C says if n is an element of the counting numbers, the natural numbers, then n is greater than 0. Okay, so that's what we want to prove, those 3 parts. Yeah, it's kind of startling. We're going to prove that 1 is bigger than 0. Okay. So let's start over here with the proof. Let's start off with part A. We're going to let A be a real number. We want to show I made a mistake in stating A. A is not true the way that it's stated. If A is a real number, then A squared is greater than 0. That's not true, because A could be 0. So here I need to make an adjustment. With A being different from 0, then A squared is greater than 0. Oh. Sorry about that. So we let A be a real number, so I'm trying to prove part A, with A being different from 0. We want to show A squared is greater than 0. I had a very traumatic experience teaching today. One of my students was wearing an Auburn shirt. So I called security. But apparently there is no campus rule against someone wearing that type of shirt. So I've initiated one. We'll see. All right, look. What we're trying to do is show that A squared is greater than 0, where A is a real number and not equal to 0. And because we're assuming that A is different from 0, we have really two cases to consider. Remember, by the order property on R, the third step was if you give me a real number, it fits into exactly one of 3 categories. It's 0, it's a positive number, or is the additive inverse is a positive number. So there are 2 cases to consider. One, this case 1. Well, we know A is different from 0. That means that A could be a positive number. And one of the facts that we proved earlier was if you're positive, then you're greater than 0. And we also have proven the fact that if you multiply an inequality by a positive number, it retains that inequality. So here, I know that A is greater than 0. So I'm going to multiply both sides by A. So A times A has got to be greater than 0 times A. I'm multiplying both sides of this inequality right by A. Thus, that tells me A squared is greater than 0. So the statement is true in this case. Well, what about the other case that we could have? Case 2. What is case 2 going to be by the order property? Minus A is a
positive number.
all right, that's what it is. So what that says is that minus A, by the fact that we did earlier, is less than 0. I'm sorry. Minus A is a positive number, so that means minus A is greater than 0. Okay. So it's not going to involve the fact that we had earlier. So I'm going to multiply both sides of that inequality by minus A. So that says minus A times minus A is going to be greater than 0 times minus A. But minus A times minus A can be shown to be A squared. So A squared is greater than 0 if this side is 0. Is that okay with everybody? Okay, so here I'll make a conclusionary statement, so I'll say, so in all cases, in all possible cases, A squared is going to be greater than 0. And that's the conclusion that we want to get. So that ends part A. Before I move on to part B, or 1 greater than 0, let me look at another way of proving case 2. The reason I'm going to look at another way of proving case 2 is that really I'm going to assign a homework assignment that has to do with minus A times minus A really being equal to A squared, or being able to be written down as minus 1 times A times minus 1 times A, and the two minus 1s give us, multiplied together, give us 1. So we just get A times A. But I'd like to do it another way. So here's case 2, alternatively. At least I think it. Suppose minus A is a positive number. Okay. Then, our fact that we did earlier was we showed that A was less than 0. Is that okay? Now, we had proven in a theorem, one of the parts, so A is less than 0. If I multiply both sides of that inequality by A, I'm multiplying by something less than 0. And when you multiply by something less than 0, you have to switch the direction of the inequality. Is that okay? Thus, and that's by a fact we proved earlier, A times A will be greater than 0 times A. So that says that A squared is going to be greater than 0. So this is an alternative way of handling case 2.
So basically, gets rid of the minus sign, so it's easier.
Right, and I haven't proven this, and I'm going to give it an assignment. As a matter of fact, the assignment now, because I've proven it in another way, might be able to use this fact that a squared is going to be greater than 0. Is that okay? So the assignment, this fact, because I've proven it another way, does not depend on that homework assignment. Okay? So this fact can be used possibly to prove the homework assignment. Part B of the theorem. Okay. Part B of the theorem was the Starling one. Okay. Starling, that's what we're going to show. We're going to show 1 is bigger than 0. Okay, well, first of all, what is 1? Melissa, listen to my question. What is 1? I mean, we had it defined. There is something that we've said that says this is 1. 1 is a number such that if you multiply it by anything, you get the anything. Is that okay? That's the property 1 has. Except there was something else written in these algebraic properties of R about 1. 1, it has that property, and 1 is not 0. Okay. So that's what we have. Okay. So we want to show that 1 is greater than 0. Note, 1 is not 0. Also, 1 is the same thing as 1 times 1. Because 1 right here, where my finger is the multiplicative identity. If you multiply 1 by something, you just get to something. So 1 times 1 is just 1. Is that okay? Thus, 1 is equal to 1 squared. And what did we just prove in part A? That if you give me a real number that isn't 0, I'm giving you 1. It's not 0. If you square it, it's got to be greater than 0. That's the proof. Outstanding. We have part C to do. What was part C? Part C is if you give me a natural number, it had to be bigger than 0. So we let n be an element of natural number. So you give me any natural number. We want to show n is greater than 0. This is a statement about any natural number. And one of the proving techniques that we had early on about proving statements about any natural number was that we can often try to prove this using induction. So here's what I'm thinking. So it's a proof, and I'm going to say, so by induction, we note that the statement is true for n equal to 1 by part B of this theorem. Hey, look, we want to show that if n is equal to 1, 1 is greater than 0. We already know 1 is greater than 0. That's what part B was. Part B, we said 1 is greater than 0. Okay. Now, for the second part for induction, we suppose the statement is true for n equal to an arbitrarily fixed number, k. That is, we're assuming that k is greater than 0. What do we have to show?
K plus 1 is also true.
And so that when n is equal to k plus 1, the statement is true, also true. That means that we need to show that k plus 1 is, what's the statement for n equal to k plus 1?
But it's positive.
Yes, that's right. The way that we're writing it is greater than 0. That's right. we must show the statement is true for n equal to k plus 1. That is, I'm being very careful on what I write here. I'm being very formal. Maybe slower than what I would be normal, but we'll start this course. That is, we want to show k plus 1 is greater than 0. And here's the way I'm going to do it. I'm going to say, well, since k is greater than 0, that's what we're assuming. Since k is greater than 0, k is a positive number. That's by a fact that we prove. Since 1 is greater than 0, then 1 is a positive number. And what do I know if I add two positive numbers? That's right. And so by the order property, on R, that tells me that k plus 1 is a positive number. But that's equivalent. If you're a positive number, that means you are greater than 0. That's right. And that's what I set out to prove, okay? Thus, by induction, if n is the element of natural numbers, n is greater than 0. And so that proves this part of the theorem, and that was the last part of the theorem. So that's the whole theorem. Okay. I want to look at two more theorems having to do with inequalities. The first one got a couple parts. It says if a times b is greater than 0, then either a is greater than 0 and b is greater than 0, or 2, a is less than 0 and b is less than 0. I'm going to do this by cases based on that. So here's my proof. So let's let a times b be greater than 0. The first thing I want to talk about, I'm going to be considering, first of all, an overall scheme of this proof. I'm going to be considering a. So a is a real number. We got three options for it. It's either 0, it's a positive number, or minus a is a positive number. And we've translated that into three situations now. That if you're a positive number, that means you were greater than 0. And if minus a is a positive number, that means a itself was less than 0. So a is either greater than 0, equal to 0, or less than 0. That's the three situations we have. Note, if a were equal to 0, then a times b would equal to 0. Because 0 times b is 0. But that's a contradiction. Because we know a times b is greater than 0. So, a cannot be 0. So a can't be 0. That's one thing I've learned. Now, so we consider only two possibilities for a. Okay, so what are the two possibilities?
Well, A is greater than 0 or A is less than 0. Okay, that's going to be my cases.
Case one. If A is greater than 0. Okay, what are we trying to show? So in this case, we'd like to show that B has to be
Greater than 0, that's what we got to show.
okay. Now, here I'll say, note, B cannot be 0 because if so, then A times B would be equal to 0 because it'd be 0 times A, which is 0. So I know B can't be 0. So we will consider two subcases. So in this case, I'm going to have subcase 1, and it's based on B. I know B can't be 0, so B could be positive. Now, if B is greater than 0, then A times B will be greater than 0. Subcase 2. If B is less than 0, then if I multiply both sides by A, I get A times B is less than 0. But that's a contradiction. Okay. So, in this case, B cannot be less than 0. So B can't be 0, and B can't be less than 0. Thus, we know B has to be greater than 0. So A has to be greater than 0, and B has to be greater than 0. In this case. Now, case 2, if A is less than 0, then, here I'll not say if, I'll say let A be less than 0. Then, B can't be 0 as A time, because if B were 0, A times B would be equal to 0. That's not happening. Also, if B were greater than 0, in this case, then A times B, so I'm thinking about multiplying this inequality, A being less than 0, by B, so A times B will be less than 0, which is a contradiction. So when A is less than 0, B has to be less than 0. That's only the case that's left. Thus, we've proven the statement is false. If A is positive, B had to be positive. If A were negative, then B had to be negative. I'd like to write up a corollary, a kind of analogous statement to the one that we just did.
I won't prove it, but I'll just state it.
As a corollary, if A times B is less than 0, then either part 1, A is less, or I'll say greater than 0, and B is less than 0, or part 2, A is less than 0 and B is greater than 0. For here, the proof is simple. And I won't do it. To the previous proof. I'd like to prove one other thing before we go on to talking about absolute values. And so here's the statement. It says, if 0 is less than or equal to A, which is less than epsilon, for all epsilon greater than 0, then A had to be 0. Here, I'll write that, yeah, for all. You want to do a proof of this? Before I do a proof, let me read that statement again. What is this statement saying? It's saying the following. It says, hey, if you got some number that you know is bigger than or equal to 0, but yet that is smaller than all positive numbers, well, it had to be 0. Is that okay? That's what we're saying. So let's look at the proof of that. Makes sense. Let's look at the proof.
You said it one more time and it's good.
Sure. It's easy to say. So look, if you're looking at number A that has the property that it is greater than or equal to 0, and for any positive number that you give me, it's going to be less than it, then that number A had to be 0. And the way that I'm going to prove this is by contradiction. So here, I'm going to say, suppose A is not 0. I guess the way I should say it is, suppose A is greater than or equal to 0 and A is not 0. So how do we prove something like contradiction? I didn't say it the way I want you to get it. Sorry, one more time. Suppose 0 is less than or equal to A and it is less than epsilon for all epsilon greater than 0. Also suppose A is different from 0. All right, now the question is, what am I trying to do? I'm trying to prove this statement by contradiction. How do we prove something by contradiction? The way we do that is we assume the if part. So I need my number to be, that we're talking about, to be greater than or equal to 0, but yet is less than any positive number you give me. And we assume the opposite of what we're trying to show. So suppose that A is not 0. And what we're going to do is logically progress to get a statement that we know to be false. Okay? That's what we're going to do based on these assumptions. Okay? This first assumption I had to make so that the statement applies. It's this statement that we're going to be able to contradict. Okay? Logically, we get a conclusion that is not correct, and therefore this has to be wrong. Okay. Well, since A is greater than or equal to 0 and A is different than 0, then that just means that A had to be greater than 0. Thus, 1/2 times A is going to be greater than 0, as 1/2 is greater than 0. Look, I don't want to pull anything of I don't want to do something without verifying it. So I'm going to go here to the sideboard and say, I don't know that 1/2 is greater than 0. I know natural numbers are positive, right? But how do I know that 1/2 is greater than 0? Well, here's what I'm going to do. So in the midst of this, I'm going to prove something called a limit. That's a statement that we need to prove something else. That's what that word means, limit. If A is greater than 0, then 1/A is greater than 0. I'm going to prove this by contradiction. So, suppose A is greater than 0. Also suppose 1/A is, what am I going to say here?
Less than or equal.
That's right, Joe. That's what I'm saying. Then, and I'm going to skip a little steps. Here, that's going to imply that A times 1/A, I'm essentially multiplying this side by a positive number. Okay, and I'm going to get this. A times 1/A is going to be less than or equal to 0 times A. Is that okay with everybody? I'm kind of skipping some steps, but this is what we get. Thus, 1 has to be less than or equal to 0. And I know that's a contradiction. The word suppose. The steps that I'm skipping is breaking this into two cases. 1/A is less than 0, or 1/A equals to 0. And in both cases, when you multiply it by A, you're going to get this statement result. That's a contradiction. So we must have assumed something wrong. What we assumed was that 1/A was less than or equal to 0, so 1/A has to be greater than 0. How does that help me? I know 2 is a positive number. It's greater than 0, because every natural number is greater than 0. I proved that. We proved it. And so its multiplicative inverse, 1/2, has to be a positive number. That's why I can say what I did in our proof. Okay? That's the reason. I don't have good eyesight, so I'm sorry. Okay, so where were we? We're trying to do this by contradiction. So we have A/2 is greater than 0. By assumption, okay, look, what is one of our assumptions? Is that if you give me any positive number, A is less than it. Well, I tell you one positive number, A/2. A is going to be less than A/2. That's not true. Okay? If you give me a positive number, it's not less than its half. Is that okay? That's a contradiction. Thus, we must assume something wrong, and what we supposed that we had control over was that A was not equal to 0, so that means A must be equal to 0. All right, the next thing that I want to talk about is the absolute value function. As I move on, one thing I want you to do is I didn't fill in the detail here, okay? So I'm starting to skip away just a little bit from some details. Why is it the case that if A is positive, or greater than or equal to 0, why is it that it can't be half A if A is, if we say A is positive, why can't it be less than half of itself? Think about that, try to prove that. Okay? Let's skip to why that's a contradiction. Okay, I want to give a definition for the absolute value. So, let A be a real number, then the absolute value of A is denoted by A in double bars and given by, so here's its definition, the absolute value of A is equal to, well, books define it one of two ways. It's either A if A is greater than 0. It's 0 if A equals to 0. And it's minus A if A is less than 0. Which is the same thing, so here's the other way that a book can define it. It's A if A is greater than or equal to 0, and it's minus A if A is less than 0. So those are the two traditional ways. Let's look at a couple of examples. The first one I'm going to say is, what's the absolute value of 3? Well, the answer we know. It's 3. Now, how do you read this definition to give it to you? Well, here's what it says. Let me tell you the right phrase. The absolute value of something is either itself, I'll put it here, it's either itself or it's minus itself. It's itself if itself was greater than or equal to 0. It's minus itself if itself was negative, less than 0. Is that okay? So here, the absolute value of 3, it's either 3 or it's minus 3. It's 3 if 3 is a positive number. Is 3 a positive number? Okay. Another example is the absolute value of minus 7 equals to 7. Why? Well, the absolute value of minus 7 is either 7 or minus 7. Is that okay? It's minus 7 if minus 7 is greater than 0. But minus 7 is not greater than 0. Is that okay with everybody? And so that tells us that minus 7 must be minus a minus, the absolute value of minus 7 must be minus a minus 7 as minus 7 is less than 0. And so we just get minus a minus 7 is 7. That's what we do. Okay. Well, I'd like to prove the fact about absolute values. And the first fact that I'm going to prove is this. Theorem. It's got several parts to it. Here's part A. It says the absolute value of A times B is equal to the absolute value of A times the absolute value of B. And that's true for all A, B, element of R. Notice the notation. For all is this upside down capital A. Part B. The absolute value of A squared equals to A squared for all A element of R. Part C. If C is greater than 0, then the absolute value of A is going to be less than or equal to C, if and only if minus C is less than or equal to A is less than or equal to C. Part D, minus absolute value of A is less than or equal to A, which is less than or equal to the absolute value of A. And that's true for all A element of R. I think I got time to do part 1. No, I said that one of the things one person who approved is kind of glaring. 1 is bigger than 0. I don't know what people would think. Uh-oh. I don't think I got this on the board, on the tape. Here's our theorem. Let me give everybody a second to write that down. It's not here. That's the theorem we're going to prove. 1 bigger than 0. So I kind of think, if you go home and you tell somebody, in our high-level math class today, we proved 1 is bigger than 0. They're going to say, that doesn't sound too high level. But it is. The reason why, the structure why it's true. It's not somebody telling you a fact. It's we're saying from previous facts we can prove this. All right. So that's the statement we want to prove. It has 4 parts. We're going to do part A and then probably call it quits. So here for the proof, part A, we're going to let A and B be elements of real numbers. So if you want to prove a statement for all real for any 2 real numbers, okay, you just say, well, let me take 2 generic real numbers and prove a statement for those. Okay. Now here, we consider the absolute value of A times B. That's what we consider. Okay. And we'll have some cases. Here's case 1. If A is greater than 0, then here's subcase 1. What if B was greater than 0? Then what can you tell me about A times B?
Greater than 0.
So, the absolute value of A times B, we're talking about taking the absolute value of something that's greater than 0. So the answer to this is just itself. Also, what is the absolute value of A in this case? Well, A is greater than 0, so the absolute value of A is A. And, well, B is greater than 0 in this subcase, so the absolute value of B is B. Thus, the absolute value of A times B equals to the absolute value of A times the absolute value of B in this subcase. And we want to prove this part. And that's the statement we wanted to show. So in this part, it's true. Let me do subcase 2. What's subcase 2? Well, B, I'm having kind of fixed in this case that A is greater than 0. So we're really now, in this case, having subcases based on B. So B could be greater than 0, or B could be equal to 0. Then A times B is equal to 0. So what's the absolute value of A times B?
0.
Is 0. Also, if you look at the right-hand side, the absolute value of A times the absolute value of B, what's it equal to? It's equal to the absolute value of A times the absolute value of 0, which is the absolute value of A, a real number, times 0. Well, what's a real number times 0? 0. So look, the absolute value of A times B is 0, and the absolute value of A times the absolute value of B is equal to 0. So they're both equal to 0, so they must be equal to each other. What time is it? Yes, ma'am. Why don't we stop at that point then, and we'll finish up next time. You think about why A has got to be less than A over 2 is a contradiction, okay? And I'll show you why next time as well. I'll probably give you an assignment too. Thank you very much for your time and patience.